Okay, anyway, so what we can do is, as I was mentioning, I'll try to present you some experimental configurations which people have analyzed, and the results of which depend on essentially the quantum properties of light. Okay, remember I was mentioning that in interference experiments, if you have a knowledge of the path of the photon, single photon interference, if there is a knowledge of the path taken by the light in an interference experiment, you lose the interference pattern. And in fact, you don't need to observe the path of the photon. You don't need to do an experiment to observe the path of the photon. The existence of information about the path in the experiment destroys interference. Now, I'll show you a very interesting experiment which was performed in 1991 and which shows some bizarre results. Okay, here is the experiment. So I have a beam splitter. This is a pump light. So then I have two mirrors here which make the beam go horizontal. Here I have a nonlinear crystal which generates parametric down conversion, two photons, signal and idler. Signal goes here. Okay, this part goes to another nonlinear crystal and generates another pair of signal idler. Okay, let me draw this. This is signal 1, idler 1, signal 2, idler 2. And there is a detector here and there is a detector here. This is one crystal here, this is another crystal. Okay, so the experiment is as follows. Here is a pump laser. Yeah.
Sir, when we had done the analysis, was it not that the signal and idler would propagate along the same direction as the input?
We were looking at a configuration where the phase matching was like that, but it's also possible that the phase matching takes place with non-collinear propagation of signal and light. Then the phase matching condition will become vector equation. Kp vector is equal to ks vector plus ki vector rather than all the vectors being parallel to each other. So in many geometries, the pump comes in and then generates a signal idler pair which are not propagating in the same direction. Okay, so what happens is the pump comes from here and the pump is weak enough so that, let me assume a single photon of pump comes here. It goes into superposition state of being in this arm and in this arm. Then this arm goes through a nonlinear crystal generating a signal idler pair. This arm goes through a nonlinear crystal, same identical nonlinear crystal generating a signal idler pair. And this mirror is movable. There is a beam splitter again here which combines this signal path and this signal path and goes into the detector. Okay, now here is the experiment. I make sure that this idler path and this idler path are exactly overlapping. Remember, this crystal is transparent to signal and idler. So this idler photon generated here will pass through the crystal without any effect. This idler generated by this crystal also propagates in the same direction. So I ensure in my experimental setup that this idler photon and this idler photon are exactly overlapping, so that when I receive an idler photon here, I do not know whether it got generated here or it got generated here. Okay. So now I measure the intensity here as a function of position of this mirror. I see interference. What is happening is that the signal arriving here can arrive in two different paths. It could have got generated here and along this path, or it would have got generated here and goes along this path. There is only one pump photon coming in. It goes into superposition state. That superposition state leads to a superposition of signal idler pair generated here and a signal idler pair generated here. The signal pair are made to overlap on a detector. The two idler photons are exactly overlapping, and there is no information as to whether this idler came from this crystal or this crystal. Okay, so what happens is, because the signal arriving here could have arrived from this crystal along this path or from this crystal along this path, the probability of arriving of the signal here is the sum of the amplitudes of this path, and then if you vary this mirror's position, you find interference effect here. Please note, there is only one signal idler pair, because there is only one pump photon entering, there is one signal idler pair being generated, but it is in a state in which the signal idler pair could have come from here or from here, and there is interference pattern fringes here. I block this beam. What is the effect of blocking this beam? If I receive an idler here, I know that the signal that's coming here is from this crystal. If I receive a signal here and no idler here, I know the signal has come from this crystal. As I move this mirror, there is no interference. Please note, I have not touched the arms of the signal. All I have done is that there is information in my experiment of the path of the signal and which destroys interference. If I don't block it fully, but if I block it, say I put a filter which passes 10% of the incident idler, there is 10% uncertainty. Interference fringes come back with lower contrast. So what is actually happening is, so this person who is receiving this light here, in fact, he does not have to put it in the detector. You are doing the experiment, and suddenly I block this beam, your interference is lost. That's because in this experiment, there is information about the path of the signal that arrives on this detector. This is a very interesting paper. You should, those who are interested should refer to this paper, Zhu, Wang, and Mandel. Physical Review Letters, 67 volume, 1991. Please note here, I'm not disturbing the signal at all. In no way am I touching the signal anywhere. All that I am doing by putting this block here is to create information in my experiment which will help me to identify which signal has come on this detector. What is the path taken by the signal? And that destroys interference. Some bizarre experiment, and so this is a very, very interesting experiment which shows the importance of information of the path of the signal photon in this experiment, which destroys interference. So interference effects, I can regain interference effects if I remove the block and introduce in my system no knowledge about which signal, whether the signal was generated here or here. In fact, if I misalign this crystal, and if I misalign the crystal so that this beam comes out separately compared to this beam, I will lose interference. Because then I know again which crystal has generated the signal. Okay, so that's a very, very interesting experiment. It's discussed in this paper here, which you can entertain yourself by reading this and see how quantum effects are playing at this stage here. Okay, the other experiment which I wanted to mention is based on our analysis of the following problem. We had looked at a state in which I had one photon coming in from here, another photon coming from here. So what was the output we had calculated? Remember, we found an output which was 212,304 plus 0,324. That means either both photons arrive in path 3 or both photons arrive in path 4. The probability of one photon in 3 and one photon in 4 is 0. Now, an experiment based on this was conducted by again a group from Rochester, and here is the experiment. Here's my nonlinear crystal, this pump. It generates two identical photons. I have a detector here, I have a detector here, and I do coincidence counting. So this is the paper. Again, physical review letters 59. Okay, what the experiment is essentially, you have pump coming from here, generates a pair of photons, degenerate down conversion. Then these two photons are actually remixed on a beam splitter. Now, you see, when we discussed parametric down conversion process, we assumed perfect phase matching. But suppose I don't have perfect phase matching, what will happen? I will still generate pairs of photons, but with a slightly lower efficiency. Which means if I take a single frequency pump, omega p is equal to omega s plus omega I. I need to satisfy, remember, two conditions. Omega p is equal to omega s plus omega I, and kp is equal to ks plus ki. Phase matching condition. This is nothing but omega p, and p is equal to omega s ns plus omega I ni. So I need to solve these two equations. But remember, this has infinite number of pairs of omega s, omega I. One pair, which will also satisfy this equation, satisfies both these conditions, will have maximum down conversion efficiency. There will be other pairs of omega s, omega I which satisfy this condition, but which satisfy this approximately. So their efficiency will be slightly less. So even if I take a crystal and if I launch a single frequency pump, I will not generate one monochromatic omega s and one omega I only. I will generate a range of frequencies, which means there will be the probability of one particular pair is much higher, which is satisfies the phase matching condition, than other pairs of photon frequencies, which will still be satisfying this equation, but approximately satisfying this equation. So what I get out is a multimode single photon state. It's a wave packet coming out. It's a photon wave packet, because there is a spectrum of frequencies of the signal which is coming out. There is a spectrum of frequencies of the idler which is coming out, and a spectrum of frequencies, but there is only one photon of the signal and 1 photon of the idler. So this will be a single photon multimode signal state, and this will be a single photon multimode idler state. The width of those duration will depend on the spectral width of the emission process. If the spectrum is broader, the pulse, the wave packet will be narrower. If the spectrum is narrower, the wave packet will be broader. It's a Fourier transform relationship between the time space and the frequency space. So if you have a broader spectrum of generation of down conversion, you will have a narrower pulse, a narrower width single photon wave packet. Otherwise, if you have a narrower spectrum of down conversion, then you have a broader wave packet. Okay, so what is actually happening in this experiment is there is one wave packet coming from here, another wave packet coming from here. Okay. Now you see that when we do this, to interpret this experiment, actually both the photons should arrive at the beam splitter at the same time. Otherwise, there is no interference. If I make sure that this path is shorter than this path, then this photon will arrive, because they are both generated simultaneously in the crystal. This photon will arrive slightly earlier compared to this, and when this photon wave packet arrives, there is no interference. It splits into two halves, or it goes into a state of being here or here, and similarly, when the next one arrives, it also goes into a state of being here and here. If I move this mirror, or if I move this setup so that I change or I make the path differences exactly equal, when the path lengths become exactly equal, then both the down converted photons will arrive at the same time, and both of them will go into one of the arms, according to this picture. So what people do is, I get a signal from here, and find out over a small window of time whether I see any coincidence. That means whether both detectors click at the same time. If both detectors click, one of them has come here, the other one is gone here. But if this state is generated, I should have no coincidence, because both photons will either go here or both photons will either go here, and so there will be no coincidence. So if I plot the coincidence rate versus the position of this beam splitter, I see a dip. This position is the position of this beam splitter where both wave packets arrive simultaneously on the beam splitter. And as you move away from this position, one of them arrives earlier than the other, and so within the open window of this detector, one of them goes here and the other one goes here, for example. So there is a finite probability of coincidences between the two detectors, but if you come into a state where both of them arrive simultaneously on the beam splitter, you will either have both the photons here or both photons here, and the coincidence becomes minimum.
So this time window detector that we are talking about is due to the relaxation time of the detector or something like that?
Or the time for which I keep the detector open. I open the detector and close it simultaneously, both of them, and that has to be a finite duration, maybe nanosecond, maybe some time, within which any photon that arrives is detected by the detector. It cannot be instantaneous detection. Okay, so within that time window, if the photon arrives here and here, it detects as a coincidence counting. Now the interesting feature about this is, if the wave packet coming from here is very narrow, the width of this peak, the width of this dip is very narrow. Because suppose this width is 20 femtoseconds. If you delay, if you change the path length between these two by 20 femtosecond time delay, you will have coincidences. So you have to position this as accurately as possible so that within the path length or the time taken difference between these two is less than the wave packet width. So if it is 20 femtoseconds, I can actually measure this to an accuracy of 20 femtoseconds. These detectors are not at that speed at all, operating at that speed, but I can actually measure time delays, extremely small time delays, by using the quantum interference effects. This is called the Hong-Wu mental dip. They were the first ones to do this experiment. This dip is called the Hong-Wu mental dip, and it actually tells me how closely identical these two photons are. If this was signal and idler, which was different frequencies, this is not the right way, because this photon is different from this photon. The frequencies are different, so I cannot add them like this. I have to define more number of modes. This is one frequency mode, this is another frequency mode. This doesn't work. So this is one way to make. So this is a degenerate process in which an omega p comes in here and splits into omega p by 2 and omega p by 2, and then I make them interfere. And this is very interesting, because then I can actually measure very, very small time delays. And this is another a way of checking whether the photons that are generated are identical, etc., etc. Now, because I can measure such small time delays, people have used this effect to measure what is the velocity of a single photon inside glass. Okay, so all I need to do is have an experiment in which in one of the arms, so I set up an experiment in which there is a position of the beam splitter which gives me a dip, minimum position. Then I insert my glass in one of the arms. Now I have to readjust the position of the beam splitter to come back to the same minimum position, and the distance by which I move will tell me an indication, give me an indication of the velocity of the photon, single photon. And if the wave packet is sufficiently broad, it has been found that the velocity of the single photon is the group velocity that you calculate classically. If a single photon is propagating through glass as a wave packet, and the velocity of that single photon is actually the group velocity of light, because now it's a group, because it is not a single frequency wave, it's a wave packet, and that packet travels at the group velocity inside the medium. Now, what is interesting is that people did this experiment to measure how much time light takes to tunnel through a barrier. Remember, if I have, for example, if I have a prism, and if my angle of incidence is more than the critical angle, this theta is greater than theta c. This total internal reflection, but if I bring another prism here, part of the light gets transmitted. This is optical tunneling. It's also called frustrated total internal reflection. This happens because there is an evanescent field on total reflection. When you have a wave totally reflected, there is an evanescent decaying field which is propagating like this. This is N1, this is N2, N1 greater than N2. And this is called the evanescent wave. If you bring another medium close by which interacts with this evanescent field, then light can actually go to the other medium. This is optical tunneling. It's, in quantum mechanics, particles can also tunnel. Okay, so an alpha decay is a process in which they're tunneling out of the nucleus, from the nucleus. Okay. The question is, how much time does the light take to tunnel across the barrier? And please remember, these barriers have to be very close, because if they are far away, there is no tunneling, because you will be too far away between the two interfaces so that you don't pick up the evanescent field at all. So you have to come very close. But if you come very close, the distance is very little, so you need to measure a very small time. This is an ideal experiment to measure this tunneling time. And so what was done by this group, here is the paper, Steinberg, Kwiat, Chow, again physical regulators, 71, 1993, 708. Okay, so parametric Dunn conversion is very useful. So here is my tunneling barrier. Okay, so I can move this mirror to adjust the time. Now, normally I would have expected that suppose there is a position without this barrier, suppose I could adjust so that the medium is still there, but it is not tunneling, it is propagating through. I will have a certain position of this mirror where I get this dip, which means both the photon wave packets arrive simultaneously at the nucleus. With tunneling, I would have expected this to be moved away or closer. If it travels slower, if it takes some time to tunnel through, right? So I would have had to move closer, right? When they did the experiment, they found it has to be moved away. It looks like light is tunneling at more than velocity of light in free space. Superluminal tunneling. This experiment is possible because of extremely small time scale that is measurable using this Ongo metal dip. Of course, there are arguments and discussions on what is the meaning of tunneling time and what is it may happen. It may so happen because it is a wave going through. If you have a wave packet going through a medium, the velocity of the wave packet depends on how the velocity of individual frequencies in the wave packet travel. What is the velocity of individual wave packet? Individual wave trains of the wave packet. And it may so happen because of the dispersive effects that even before the peak of a wave packet enters the medium, a peak has already come out. It looks as if the time taken is negative. But what is actually happening is there are distortion effects on the wave packet or other effects that are taking place, which are making you measure a velocity which is faster than velocity of light, but there is no information transfer at greater than velocity of light. See, tunneling means you have a certain fraction of the incident light that is going through. Remaining is all reflected back. In this case, if I keep a distance so that the tunneling is 1%, 99% of the incident light is reflected and there's only 1% transmitted. So what you are measuring here is that 1% of that transmitted light which is forming this dip, and there are a lot of analyses and sort of estimations and calculations of what is the meaning of this superluminal tunneling, etc. But what is interesting is that this kinds of experiments help one to experimentally see effects which are otherwise not possible. How do I otherwise measure time scales of less than a few femtoseconds or tens of femtoseconds, especially when in problems like this where I need to measure the time taken by light to propagate through a very, very small distance. Yeah.
So in general, if there is no frustrated total internal reflection, then is it true that all the energy is reflected?
Yes.
100% is reflected.
Yes.
Now, then also there is an evanescent wave.
Yes.
So some energy should be. How is it possible that once the wave has been converted to evanescent wave, and then we say that it has no energy, it is evanescent?
No, it has energy. It has energy propagating parallel to the interface.
Reconverts into propagating wave or something?
No, it's a propagating wave. I have this interface. I have wave coming from here.
Yeah,
I have a reflected wave.
Vertical direction propagating in the other direction.
Yeah, but it has energy, no? I can actually measure energy. If I put a detector here, I will detect energy. Only thing is, it's not leaving. It's attached to the surface. Now your question is, how can there be total reflection when there is energy here?
Uh, does the reflected beam has all the incident energy?
Yes.
Then
Yes. The problem arises because normally we are dealing with infinitely extended plane waves. For infinitely extended plane waves, there is no beginning. So I will say this evanescent wave has come from here. Where has this come from? This has come from here. This energy is continuously propagating. This energy is continuously getting reflected. If you ask me where this has come from here, this has come from, you go back. Okay, now, how do I solve this problem? So I say, I take a beam of finite width. See, the problem is, as this wave hits this boundary, it needs to set up boundary conditions, satisfy boundary conditions. So it needs to have an electric field in this other medium. Otherwise, I cannot satisfy boundary conditions. So the field enters, sets up the boundary condition. So in the initial portion of the beam, there is less reflection than total. Once this field is set up in the rarer medium, no more energy is entering to set it up because it's already set up. From this point onwards, everything is reflected. At this point, when the beam ends, there is still an evanescent field, which will have to set up a boundary condition on the other medium. So it comes out, and the beam comes out like this. Have you heard of this? Yes. This is the Gusan concept. Now, there is another way of looking at this problem, and this a beam which is a beam is not a plane wave. It consists of a large number of plane waves in all directions. Okay, so in fact, in a beam, I cannot have total reflection because some of the components of this beam are incident at less than critical angle. They will lead to a transmission. Okay, so the problem is because of infinite extent of the plane waves that you have an evanescent field which is carrying energy, but the reflection is still total. Okay, I think that's all I would like to present as some interesting experiments. If you have any questions, queries, we can address them right away.
Sir, in the tutorial that you just given, there was a question regarding calculation of the probability of photoionization, the last one.
Mm-hmm.
So that was
For two frequencies.
for two frequencies.
Yeah.
So I did it and I was not able to get the peaks beat by them.
Why? Your electric field will be the first electric field plus the second electric field operator, right? So the electric field operators would be I square root of h cross omega 1 by 2 epsilon 0 v a1 minus I omega 1 t minus k1 z minus a1 dagger exponential I omega 1 t minus k1 z. Similarly for E2. And then you have to calculate the expectation value. What did I say? I have a superposition of single photon states. So what is the state you will take? So what is the state you will take?
0, 1, 1, 2, and 1.
Yes. Where 1 is this frequency, 2 is this frequency. And then you calculate W1, which is psi E1 minus plus E2 minus into E1 plus plus E2 plus. So these all will contain the dagger operators. So this part is E1 plus and this part is E1 minus. This part is E2 plus, this part is E2 minus. So all the minuses are here, plus are here. So you will have A1 dagger, A1 dagger A1, A1 dagger A1, A2 dagger A2, A1 dagger A2, A2 dagger A1, etc. So you should get. And this psi is this state.
So there will be two number operators, because A1 dagger A1, A2 dagger A2.
Yes.
And there will be one term containing A1 dagger A2 and A2 dagger A1.
Yes.
Okay.
Yeah.
These are the four terms that will be there.
Yeah.
Now, in these four terms, the term containing A1 dagger A2 and A2 dagger A1
will give you intensities. No, sorry, A1 dagger A1 and A2 dagger A2 will give you intensities.
That is fine. The term containing A1 dagger A2 and A2 dagger A1, when they operate on this side, they will give me exponentials, basically.
Yes.
They'll leave
Two exponentials you will get. Yeah.
And when I sum them up, I guess get
Cosine.
just a cosine term.
Yeah.
So that is not essentially the beats. Beat pattern is basically product of two cosine terms, and that would be
No. What is the cosine term you get?
omega 1 minus omega 2 t.
So cosine you will get omega 1 minus omega 2 t minus k1 minus k2 z.
Since they are propagating in the same direction.
Okay, so you assume z is equal to 0.
Yeah.
Okay, so this. So what is the meaning of this statement? So if I have a detector here at this place and the waves, this state is coming from here, at certain intervals of time I will have more intensity, more probability, at certain intervals of time I have less probability. That is beats. Light beats in time domain. Beating of light waves, not sound. It is like classically, if I have two different frequencies, I will get like this. This is beats. This is what exactly I am getting. At certain intervals of time, whenever the cosine is 0, whenever the cosine is plus 1, I have more probability. Whenever the cosine is minus 1, I have less probability. And the probability of detection, if I have a large number of detectors simultaneous and measuring an ensemble of states.
This would give me just the envelope function, basically.
Yeah, I know. I'm not measuring the high frequency. I can't. Yeah. Anything else?
When we had the third order nonlinearity,
Yeah.
we said that depending on the N2, there is a expansion or the frequency will increase.
Sure. Yeah.
So that means that the photons that are going to come out will have a higher or lower frequency.
The first thing is we didn't discuss that in the photon picture.
Yes,
Okay.
we did not.
Yeah. So if you send, there will be spread of wave. This. You have new frequencies generated in the medium, right? Because of nonlinearity. And if you try to measure the frequency, you will be able to measure photons also at different frequencies, arriving at.
That means the number of photons will change.
No.
So then if the frequencies are changing, then the
No, not changing. What it implies is, I have a large number of ensemble of fiber, same medium for example. I send one photon here at certain frequency. I measure a certain frequency coming out. I do the same experiment again or do another experiment. I send the same frequency photon. I measure a different frequency coming out. And if I now plot what are the number of photons at different frequencies, I will get a spectrum, and that spectrum is broader than the input spectrum. I cannot predict whether in my first experiment what is the frequency of the photon that I will measure. It will follow probability distribution, which is the classical wave packet that I will generate in my classical analysis.
But the energy has to be conserved.
Yeah.
So how is it conserved?
No, it is a four-way mixing process.
It won't be there if there is a single photon.
Sorry?
If there is just one photon.
No, but you see, there is not one wave incident. No? There is a wave which is incident with multiple photons. So what you are generating is what you're doing in that process is a general. So you see, what is the chi3 term? Gives me a nonlinear polarization proportional to E star E, right? So this is 3 waves at the same frequency are mixing. So what you're generating is the frequency omega by this process. This E corresponds to omega, this E star corresponds to minus omega, this E corresponds to omega. These 3 photons are mixing to generate a new wave at a frequency omega. So it's a mixing process. So if you're generating new frequency, obviously you're losing energy at the other frequency that you input. Just like in the second harmonic case or in the parametric non-conversion case or some frequency generation, you are generating photons at different frequencies, at higher frequencies. Obviously you're losing some photon at a lower frequency or some other frequency to generate a new frequency.
So if we have only one photon incident, then we don't observe this because there is
No. I don't know whether it is, no, not with one photon. Maybe I have to put one photon as my pump and one photon as my signal. The signal photon, will it get affected by the single photon of the pump? It means at that power levels. Single photon nonlinear effects. And there are people working on this kind of problems, but I don't. I wouldn't be able to say what will happen. Energy has to be always conserved. Okay, so I think that's it. Thank you very much.